So the other thing with the board was lexicodes, but I don't know if you want to do that now.
Well, a code is a collection of things called code words, and you usually want the code words to be sufficiently far from each other in a certain sense. So these lexicographic codes, well, first of all, a code word is an infinite string of digits going off, but you can think of it as rather like a decimal number. So this is the number 0, which really, its decimal expansion consists of infinitely many zeros, but we usually rub off those. And then comes 1, and then 2, and after some time you get to 10. Okay.
But you already had a 10 in the last digit. I mean, you'll allow any positive integer in the last digit.
Yes, with integral lexicographic codes, the digits are allowed to be arbitrary integers. Distance 3 means you're not allowed to have two code words that differ in less than 3 digits. The first word you are allowed is 1, 1, 1. It differs in 3 digits from this previous one. And now the first word that differs from both of those in at least 3 digits is 2, 2, 2. And we carry on doing that, and after a time we get n, 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 whatever n you like. And then there is a word that goes 1, 0, 1, 2. That differs from all of the ones before it in this digit 1, because they were all 0 there. And whatever number you take here can only happen once in this thing. I mean, if I take 1, 1, 1, that agrees with it in this one place, as well as the one before the point and so on. But because these 3 digits are different, it can't agree in more than 2 places with any previous one. Then after that comes, if I have 1 naught, then it's too close to this one. It only differs in the last 2 digits.
You could have 1, 1.
But you can have 1, 1. Try it. But now I can't have a 0 here because it's too close to that one. And I can't have
a 1
because it's too close to this one.
And you can't have a 2 because it's too close to the one above.
2 because it's too close to the one before it. So this must be at least 3, but 3 is okay. So there's no choice in what you do. And I discovered this astonishing fact that this lexicographic code, which I abbreviate to lexicode, is closed under a kind of addition. If you add 2 code words, you always get another code word. That's pretty obvious for the first few. If I take, say, this one and this one, then of course I'll get this one. And these are in the code, and so this one should be. It turns out, this is rather cheating in a way, that the addition is not the normal addition. And you can prove fairly easily that you add to 0 the way you usually do. And so if you take 1, 0, 1, 2 and add it to 0, these are all preceded by lots of noughts. Well, let's sort of take it 2, 2, 2. Then the sum of these 2 should be a code word.
1, 2.
And because 0 adds normally, that's 1, and this is 2. So this is something. Maybe I should have added 1, 1, 1. And then this would be 1, 1, something, something.
And it must be 0, 3.
It's got to be this one. And so you see that 1 plus 1 has got to be 0, and 2 plus 1 has got to be 3. And it turns out that, this theorem tells you what the addition has to be by the same kind of calculation as we've been doing. But then it's also got to be closed under multiplication, digit-wise multiplication. And the multiplication is really strange. It turns out that the addition is the same kind of addition that you use in the theory of the game of Nim. This really comes from games like Nim. It's also called exclusive OR by computer people. But the multiplication I don't think anybody ever saw before I noticed it. And it's rather peculiar. It turns out that 2 2s are, guess what, 3. And 2 times 3 is 1. So
3 times 3 is 2.
Yes, and that tells you that 2 cubed is 1, because 2 times 2 times 2 is 2 times 3, and 2 times 3 is 1. At the time I discovered this, it was a very long time ago now, I didn't know it was going to work. I didn't have this definition of it as I've been telling you about. I had another definition, but it still didn't seem obvious that it worked. And I got to work out the multiplication table. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. 0 multiplies in the obvious way. And so does 1. But 2 2s, as I said, are 3. 2 3s are 1. And 3 3s are 2. So that little part there is closed. If you take any 2 of 0, 1, 2, and 3, the product is 0, 1, 2, or 3. Then, sorry, that isn't a 12. That was a piece of chalk left on the board from some previous thing. 2 4s, it turns out, are 8, which surprised me a little bit, but because it was agreeing with ordinary arithmetic. And 3 4s are 12. And so I get 0, 4, 8, 12. And then, what are 4 4s? Well, it took me a good long time to work it out. And then, when I finally found the answer, it seemed ridiculous to me. And I remember I lay down on the floor and giggled and waved I was totally alone, waved my arms and legs in the air. It turns out that 4 4s are 6. And then I could work out what everything else was, what the product of any 2 numbers up to 15 was. And it's rather strange, you know.
So you use the distributive law beyond that?
Yes, it's distributive and associative and everything. It turns out, one of the things that really surprised me, I told you 2 was a cube root of unity. 8 is a 5th root of unity. And 8 squared is 10. And 8 tens are 14. In other words, the 5th roots of unity are 1, 8, 10, 13, and 14. How about 4? 4 is a 15th root of unity. How about 15? 15 is a 15th root of unity too. In fact, 4 and 15 are inverses of each other. Oh yes, that's a remark. This is actually a field. In other words, you can divide by non-zero things as well as multiplying and adding and subtracting and so on. And so that means that the reciprocal of every number here, in this new crazy sense, is another number. So what's a half? Well, I told you, 3 2s are 1, so a half equals 3. And a third equals 2. What's a quarter? A 15th. What's a 5th? I think it's 14. I'm not
or
quite
13.
sure. No, it's... Oh my God, I got it wrong. So what I said was not true anyway. So, and what you said wasn't true either, because 13 and 14 are fifth roots of unity, whereas 5 is a 15th root. I can't remember what it is.
Oh, an eighth is
An
13
eighth
or
is
14.
13 or 14, yes. And this leads to a wholly new and rather bizarre notion of addition and multiplication on the integers. And strangely enough, I got to it through thinking of these infinite games and the surreal numbers. This theory of adding up impartial games, due to Grundy and Sprague, says they all reduce to the game of nim. Doesn't very much matter what it is, but it's a simple mathematical game. And then when I extended it to partisan games, I found in particular the surreal numbers. And then the definition of multiplication for surreal numbers, I went back and looked what it would tell you if you had impartial numbers, which I call nimbers now, because they all arise in the game of nim. Well, this is the multiplication table for nimbers, and it's rather strange. And
Oh, so nimbers are different from numbers.
yes, nimbers. Here's the number. This Hackenbush game has value 3. This Hackenbush game
Has value minus.
has value -3. This one has value *3.
Which is the number 3. Is it?
Which is this, these things, I missed off all the stars in front of them, which is the nimber 3, yes. There are positive numbers, negative numbers, and nimbers, which are neither positive nor negative. They're something else again. And you can actually mix them up with each other. You know, I can consider the sum of the number 3/4 and the nimber *7. That's a perfectly respectable game. I don't know if it's respectable really, but and then there are many, 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 many other things as well, many other games. Another thing that I really liked was that, you know, the theory of real numbers was sort of formalized and reduced to set theory and so on by Dedekind in the 19th century, very famous mathematician, and it was always treated as a serious part of mathematics. And here was this much bigger theory, and it just came from children's games. And I liked that. You know, we have this saying in England, or we had it when I lived there, taking the mickey out of it, you know, making fun of something. And this made fun of what hitherto had been a serious part of mathematics. It did better than the standard treatment, and it did it more frivolously at the same time. And, you know, I've had this trouble, in a way, ever since I seriously started teaching, which is that I'm interested in rather trivial things, frivolous, unimportant, you know, games, working out the day of the week, all sorts of other things. And my colleagues, you know, at Princeton or at Cambridge, as I was, I've been at each of them for about 25 years. I must be old. My colleagues would never stoop to investigating children's games. And I had to sort of struggle to get the license to be interested in trivial things. You know, I used to sit around in the common room in Cambridge, as you well know, and I now do so in the common room in Princeton. I doodle little diagrams on pieces of paper, and they are as likely as not to be about games or some other thing of the same general type as games. And at various times I have felt sort of rather out of place or guilty for studying these things, or for wasting my time on them, you know. At Cambridge I always felt bad for playing backgammon all the time. But then somehow at Cambridge I grew up into the system, and everybody knew that I played backgammon all the time, and on the other hand, that I had discovered various interesting things, pieces of mathematics. And so I got the license to sort of do as I liked, and to hell with whether it's respectable or not.